We begin with Unit 1, Biological Molecules of Cambridge AS Level Biology. We're going to start with the properties of water. Now, normally I begin my course by showing a video from Crash Course by the Green Brothers, but they're not paying me, I'm just a fan. Water's bond angle, some of the things that are associated with this. Water's bond angle is 104.5 degrees, and methane's bond angle is 109.5 degrees. This results from the repulsion of hydrogen from unpaired electrons in the oxygen. So that forces these hydrogens together, decreasing the bond angle. But in methane, we have equidistant hydrogens, which all have the same bond angle between all the angles, and that is 109.5 degrees of angle. This is 104.5. Now this disparity has a lot of added benefits, including the particular shape of the solid water crystal, aka ice, which we will discuss in a moment. So, a quick question about definition. Which term describes the heat absorbed when a substance changes phase from a liquid to a gas? Enthalpy of vaporization, latent heat of vaporization, heat of evaporation. The answer is all above. Cambridge will call it the latent heat of vaporization. So, the specific latent heat, which is what you will be tested on, the specific latent heat is L. It expresses the quantity of energy in the form of heat Q required to completely affect a phase change of a unit of mass M. This is usually 1 kilogram for all intents and purposes. That's what you'll be working with. Of a substance, this is an intensive property. So LF is Q over M, and LV is Q over M. That is your latent heat of fusion and your latent heat of vaporization. The latent heat of fusion is the energy required to be removed from the liquid in order to change its phase completely from liquid to solid, or the energy that must be added to the solid to completely change its phase to liquid. During this time that you are adding energy and changing phase, the temperature of the water is not changing. From liquid to gas, we have the latent heat of vaporization. So we must add energy. We must add heat in order to go from liquid to gas to completely affect a phase change. So as water is boiling, we are adding heat energy, but we are not affecting a temperature change. We are only affecting a phase change. All of the energy going into the water is changing the water's phase, not its temperature. So that's the point of latent heat. Specific latent heat. And gas, in order to remove all of that energy, when we remove that energy, it will condense to liquid. So, vaporization, the latent heat of vaporization, is the change from liquid to gas and back. The difference is only a negative symbol or a positive symbol. Alright? So these are intensive properties. An intensive property of a material is a characteristic that is not dependent on the size or the extent of the sample. Commonly quoted and tabulated in the literature are specific latent heats of fusion and the specific latent heat of vaporization for many substances. So, how much energy is required to change its phase from solid to liquid and from liquid to gas, adding heat, that is often tabulated as an intensive property of that substance. So, how do we calculate the latent heat for a given mass of a substance? All we need to do is we need to change what we want to the other side of the equation. So if latent heat of fusion or vaporization is on one side of the equation, and latent heat and the heat is on the numerator and the mass is on the denominator, we want mass over on this side alone. We need to multiply, I will use a different marker, We will multiply by mass both sides. That will cancel out our mass. And we are left with heat is equal to the latent heat multiplied by the mass. Now we want mass by itself. We will divide both sides by the latent heat of fusion, of the latent heat of vaporization. And that will leave us with mass is equal to heat over latent heat of fusion, or mass is equal to heat over latent heat of vaporization. This is mere algebra. We are just moving variables from one side to another in order to find what we want, so we can make our math easier. That's all we need to do here. So that's how we would calculate it. And that's all that I'm doing here. To find my latent heat, Q, the quantity of energy released or absorbed during a change of phase in the substance. M is the mass of the substance, and L is the specific latent heat for a particular substance. Therefore, Q equals ML. Q equals LM over here. It's only part way of the movement of the variables that I did before. So either for the latent heat of fusion, LF, or the latent heat of vaporization, LV. Now, we have some other terms to define. Those other terms to define are the latent heat of fusion. While it's tempting to say the latent heat of fusion is the opposite of the latent heat of vaporization, this is wrong. It's how much energy in the form of the heat is required to change the phase from liquid to solid, or to fuse a liquid into a solid. Specific heat, or heat capacity. This is how much energy a substance can hold before it changes temperature. The exact mathematical definition is Q is equal to mass times the specific heat capacity, C, times the delta T, the change in temperature, which is in Kelvin or degrees Celsius. Now, latent heat of fusion and latent heat of vaporization, these apply to changing phase. Specific heat and heat capacity, which are the same thing, they apply to changes in temperature within a phase. So, heat capacity is the resistance to a change in temperature while the substance is still a liquid, for example. So, after it has completely changed phase from solid to liquid, and from before it has changed phase from liquid to gas, adding heat energy will get you a temperature change. How much heat energy you must add in order to affect that temperature change, that is your heat capacity. Now, more definitions. Hydrophilic and hydrophobic. Polar and nonpolar. Charged, ionic, and uncharged, non-ionic. Water-soluble and water-insoluble. Lipid-soluble and lipid-insoluble and lipid-soluble. These definitions go hand in hand, as do these. These tend to be the opposite of one another, as you can tell from polar and non, charged and un, water-soluble and water-insoluble, etc. So, hydrophilic, water-loving in Greek. Hydro, water, philos, love in Greek. So water-loving. These will dissolve in polar molecule, in polar solvents like water. Hydrophobic, phobos, fear. Hydro, water in Greek, all Greek. So this is water-fearing. These substances will not dissolve in polar substances like water. So hydrophilic substances are polar because like dissolves like. Hydrophobic substances tend to be nonpolar because like dissolves like. If they are nonpolar, then they will tend to dissolve in nonpolar solvents. If they are charged or ionic, they will be polar, almost by definition. If they are uncharged or non-ionic, then they will not be polar because there will be no differential charge as a general rule. All right? So, water-soluble is similar to this hydrophilic, and water-insoluble is hydrophobic, but that's specifically for referring to water, not just polar substances. Lipid-insoluble, lipids tend to be non-polar across the board. And lipid-soluble, they are soluble in lipids, in non-polar solvents. So you can dissolve a substance in water, but you cannot dissolve it in oil. You can dissolve a substance in oil, but you can't dissolve it in water. This is the case for many different compounds, depending on their nature of polar versus nonpolar. So, the key concept about the properties of water for the ACE exam is polarity. This is what accounts for water's ability to dissolve polar and ionic compounds and adhere to surfaces, and thus capillary action, to cohese to other water molecules, and thus its surface tension, and results in the geometric pattern upon freezing that gives the solid form of water a lower density than the liquid form of water. So, let's talk about water for a moment. The overall formation, actually let me just do this in different colors to make things easier in my life. I will make oxygen red because convention. I will make bonds black because convention. And I will make hydrogen blue because convention. So now we see that we have this positively, let's say this differently. Oxygen is a highly electronegative element. Highly electronegative elements have a desire to attract electrons. They really pull on those electrons. Hydrogen is a weakly electronegative element. That means it will give up its electrons readily. It will readily give up those electrons. So when you have a covalent bond, the covalent bond is the result of a shared electron pair. Hydrogen donates one electron, oxygen donates one electron to this covalent bond, and the same goes for here. Because oxygen is more electronegative than hydrogen, the electron pair will be closer, and it will spend more time with the oxygen than with the hydrogen. This allows the oxygen to have an overall negative charge, delta negative. And because of that, we have the orbital cloud being pulled away from the proton that is the hydrogen, and we have an overall positive charge, delta positive. We can place this with an arrow diagram like so, showing the overall dipole movement here. So we have positive charge in the hydrogens and negative charge in the oxygen. This is the beginnings of hydrogen bonding. Hydrogen bonding is the most important concept in the properties of water. This is what causes all of this. This polarity allows for hydrogen bonds. And if you are asked any question about explain why this is occurring, the answer in water, it is most likely because of hydrogen bonding. So, when you have an oxygen molecule here, and I've given up using the red because the red pen's all the way over there, all right? And you have a hydrogen over here, and you have a hydrogen over here, and an oxygen over here. Yes, I know the oxygen and the hydrogen are different sizes. I didn't say I was a great artist. The positive charge of this side to this side will attract, the negative and the positive poles of these molecules will attract one another, forming a hydrogen bond. An oxygen atom on water, can form one hydrogen bond with the hydrogen on another water molecule. So one oxygen can form one hydrogen bond. So the ability to form hydrogen bonds is extraordinarily important. So what you end up with, and by the way, hydrogen bonds are always drawn as dotted lines. They're always drawn as dotted lines by convention. That is always going to be the case. Hydrogen bonds are dotted lines, and if you were asked to